Perfect. So just so that you are all aware that these terms are now in common use and AI is fully aware. So I believe we have colleagues waiting online to present. So we are starting now this session on data spaces. And we will start with Clara Pezuela, who is Vice President of Funded Programs for FIWARE, and Alberto Abella, who is data modeling expert at FIWARE. And they will introduce the concept of data spaces with particular focus on the Data Spaces Support Center. So with no further ado, Clara, the floor is yours.
Hello, thank you very much. Can you hear us?
A bit of echo.
Can you hear us, Clara?
Yes, we can hear you.
We cannot, can you say something again? We cannot hear you very well.
Hello?
Yeah. If you could speak a bit louder, that will be very helpful. Sorry
Hello,
for that.
hello, can you hear me well?
Yes, but it will be easier if you can speak a bit louder. Yeah,
Okay,
we can hear you,
I will
but not
try.
so well. Yes.
Okay, I will try. I will do my best. But can you see my screen? That is true. Okay, so I assume that you are seeing my screen.
No, Clara, we cannot see the screen. We are seeing you, unless me. I don't know. Yeah, now I can see it. Yep.
Okay, so if you can see my screen, you can listen to me. I think it's fine. So thank you very much for this invitation. We, as it has been said, we work for FIWARE, but today we are here representing the project Dataspace 4.0, which is in charge of preparing the deployment of the manufacturing data space in Europe. So let's start then by a brief introduction about what is the concept of data space, as we are talking too much about it in the last times, and a brief introduction about the data spaces in Europe. Then I will go directly to give you some details about the data space for manufacturing. And finally, my colleague Alberto will present you one of the results that is expected from this data space initiative. So without more delay, just give you some hint about data spaces. So as a concept, a data space is a decentralized infrastructure which allows to enable data transactions between the participants of the players in the ecosystem, under a governance which regulates the relationship in a fair manner amongst these participants. So in the general scope of the data strategy for Europe, we see where the European data spaces are placed as one of the instruments in order to implement this strategy, and also where the Data Spaces Support Center, which is a coordination and support action project, is trying to coordinate and to give support to all these data spaces that are starting to emerge. So which are these European common data spaces? So far, it's this collection of 12 initiatives that are emerging in the different sectors. And one of these data spaces is the one that we are going to present today, which is focused on the manufacturing sector. But you can see that there are many others in different sectors. And as I said before, the Data Spaces Support Center is an additional project to this collection of data spaces, which has a mission to support the coordination of all of them, providing them all the tools, all the mechanisms, all the guidelines in order to accelerate the emerging of these data spaces and also their further deployment. One of the results that will be provided by this project is a blueprint with guidelines, with components, with building blocks that will be able to be used for building these data spaces under a co-creation process with all the stakeholders that are part of this ecosystem of data spaces in Europe. So the ultimate goal is to allow the data spaces to be focused on the domain-specific challenges because they want to leverage on the results that this support center is providing them in order to build their data spaces. So if you want to know more about the support center, here is the website, and either you want to get information about the different activities and results, or you want to be involved in this co-creation process, you can get access to the website and get in contact. So let's go then now to the detail of the data space for manufacturing sector, which is bringing the overall ecosystem of ongoing and pre-existing initiatives around Industry 4.0. So here you can see plenty of initiatives that are already there, and also emerging data spaces in this context that are already there. Of course, they are also getting the support from the Data Spaces Support Center. And also they have behind all the manufacturing sector, which is focused on different topics, on different challenges, and also on different subdomains within the manufacturing sector. So this project is the first stage of this data space deployment. It's a preparatory action under the Digital Europe program, which is lasting 15 months, and is expected that in 6 months, the project that will take care of the deployment of the data space will rely on the results of this preparatory action, and will be able to set up the different data spaces around manufacturing. So these initiatives is counting with the existing initiatives like Made in Europe, Connected Factories, and the EFRA, of course. So which is the mission of this data space? So basically it's based on 3 high-level missions. One is to analyze what is already there, to collect all the existing tools, best practices, and assets around the manufacturing domain that can be useful for building this data space. Second, it will deliver a kind of, or a set of blueprints with guidelines, with recommendations, with building blocks in order to allow the data spaces to be implemented. And finally, it will provide also a minimal viable framework for Industry 4.0 with all these guidelines and components as a baseline implementation for every data space in this domain. So as the manufacturing domain is quite broad and also quite fragmented, the idea is to focus on only 3 data value networks. One is predictive maintenance and everything around the asset 4.0 management, then in agile supply chains, and then in circular manufacturing. And as in manufacturing, we have a lot of subdomains. The idea is to select 5 out of the large number of sectors in manufacturing, the most priority ones for Europe at this point of time. They have not yet selected, so that's for your information. It's in the process. And regarding the ecosystems, the idea is to address both hierarchical and non-hierarchical ecosystems within the manufacturing domain. So bearing this in mind, the objectives, the concrete objectives of this preparatory action for the data space deployment is on one side to follow all the recommendations from the data acts and which challenges represent for the manufacturing sector. Then to contribute to the organic growth of the data value networks that have been mentioned before in the scope. Then to ensure that the data is shared in a trusted and secure manner across different data spaces. Be friend with the small and medium enterprises mainly, because the manufacturing sector is one of the most crowded domain with this type of enterprises, to facilitate the adoption of the data space, of course, and also to support to the digital product passport implementation. So in order to get these objectives, the idea or the outcomes that are expected are the following ones. The first is the governance models for all these complex and multi-stakeholder ecosystem. Then to provide this directory with all the existing assets, materials, toolkits, blueprints, whatever result that is useful for building these data spaces a roadmap with all the steps that you need to follow in order to set up this data space, a canvas in order to identify which is the business model behind your data space, a reference smart data models in order to ensure the interoperability across the data spaces, and the minimal viable framework that I have mentioned before. So this cannot be done only by one entity. So this project is formed by 12 partners, which are well known in this domain of manufacturing, and also supported by a plethora of other associated partners that are founded at this Digital Factory Alliance, and which is completely open to anyone who would like to join to this effort to create the data space. So everything is in the website, and if you want to join to this manufacturing community, I could also hear the address of the Data Factory Alliance. So now I give the floor to my colleague Alberto to present one of these outcomes that I have mentioned in my previous slide as a result of this preparatory action for the data space in manufacturing. So Alberto, the floor is yours.
Okay, thank you very much. You can pass the slide. So I've pasted some links that are exceeding the capabilities of the slides. So there are some point to get here. So there are 4 questions that I want to bring here. If we are going to share data into a data space, data of manufacturing, of course, but could be in other domains as well. So the first thing is, how could we describe the data that we are sharing? And are we going to do it manually, or could it make it automatically? What will happen if we are going to share data and they are coming from different data models, or we are emerging in an emerging sector and then people start defining their own data models? Or what will happen if can we ensure that a data set which is shared in a data space will be compliant with the standard? Or last question, imagine, and I've seen across other slides, there are multiple use cases in which you are based on an ontology, but the ontology is not covering everything you need. Will you capable of extending the ontology on the fly? So these are the questions that I guess has to be answered, because otherwise the promise of the data space is to be able to share data won't be fulfilled. So could you go for the next slide? So, and what we provided the smart data models, and we are emerging at the manufacturing sector, there are just 3 elements. So the first thing is when we define an object, could be representing either a logical or a physical entity, we describe just a list of attributes, their short names. We define what data types they are storing. So either it's a string, a date, an object, an array, whatever. And their definitions, the definition that could be brought from an existing ontology. But also, and this is very important, because on the contrary to some approaches to data model design, we ask mandatory an example. An example, and this is providing, I've seen some other presentations that we were discussing about, we need to consolidate the knowledge. When you are using an actual use case, you are demonstrated that you have the knowledge for dealing with this entity. And these examples that we are asking as a mandatory, we export into several other formats in order to make easy for other users to understand. And we not only export the payloads, the examples, but also the structure. We keep the structure as a single source of truth in JSON schema, but we export also in YAML, in SQL, and possibly in the coming years, in coming months in others. I have to mention that everything that we do is open license, so it's free to use, free to modify, and free to share. Of course, it's customizable to your needs. And the payloads are in many formats. And we have discovered, and today was a very interesting presentation about the skills required for modeling this data. But my impression is that very, very tough finding somebody who is expert in a field domain and also expert on data modeling. It's very tough. I don't think that this could be the right approach because these people are very strange. Very strange. So our approach is different. It's make very easy for somebody who is expert at the domain to create a data model. And once we do that, we create automatically a specification in 7 languages. Of course, we provide a search form for any of the elements, and you can see the links. And we are capable of mapping with an existing ontologies whenever these ontologies are covering. Okay. And the other thing, we are creating some elements like a spreadsheet, a mirror spreadsheet for creating a data model, for drafting most of the parts of that. And of course, you can also, we have another service for creating an actual example based on JSON or CSV examples. Could you go for the next slide? And this is what we already have, which is, let's say, quite limited. So we have several subjects. Subjects are groups of data models. And we have for manufacturing machines, for autonomous mobile robots, for the standard OPC UA, and for robotic industrial activities. And we have in progress many others. And I haven't mentioned, but it was to do it, that it's always possible to contribute to data models. In the links that I've provided, there is the link for asking permissions to contribute or to extend any of the data models. And let me go to the last slide, Clara, in which these are the, let's say, the main building blocks of a data space. And the smart data model wants to be present in 3 of them directly. So helping people to create the data models that for providing the information to others to be shared, of course, also to be searchable, to say, oh, I want to look some data sets which are compatible with this standard. And then it could be findable, and also helping on the automatic publication. We have one data set which is compliant with these data models. So, and now I have seen there is a question. Several of these questions has been resolved in the sales approach since some years ago. Okay, I'd like to see more information about that. But basically, the main goal is that our approach is data modeling is a complex question, and we cannot trust on having people expert on data modeling and a deep knowledge about one topic. So we have to lower the barrier to get the data model. And what our approach that we're providing here is not an alternative to creating ontologies, but complementary, because every data model shown here is mappable with any external ontology that is available. And that's everything that I want to say. Thank you very much, and I'm open to your questions.
I think your mic is muted.
Now, yes, but I'm not hearing anything else from the speaker.
I mean from
Does
the
anybody
room.
have any questions in the room?
Okay.
Whilst our colleagues are still connected. Yes, Gerhard, please go ahead.
Yeah, thank you for interesting presentation. How exactly do you define a data model? Because just in the context of what we've been discussing so far, we had like a hierarchy of semantics that has been also suggested and used in the DOME marketplace, for example, that goes from some annotations to basically using something like DCAT as maybe that's what you would call then a data model, to its implementation in RDFS.
No, not at all. Not at all. DCAT, it refers only to the metadata described in a data set. What we do is to describe the attributes of the data model, which is something that DCAT only refers thanks to the conforms to attribute.
So you define what the specific attributes are for the manufacturing in a list of basically a list of attributes, or how are the attributes organized?
It's better just, I'm pasting here. This is one specification, one example of the last data model that has been published, which is a mapping of the SARE for buildings. Okay, and it is a list of data models. Sorry, a list of attributes describing the data type and the descriptions. And of course, the origin and the real source of truth is a JSON schema. Thank you, Clara. I'm going to paste the link here. This is for us, this is a data model.
I'm sorry for asking. I mean, I think it's simply important in the context because we are speaking here in the context of, you know, ontology-driven systems, and you know, there are different traditions and different terminologies in.
Yeah, I fully understand. Yeah,
and I think it's kind of very important, in my view, to understand where data models like that fit into that landscape that that we're talking about here.
Yeah, it is not keeping an example all the inheritance that you can define in ontology and some of the restrictions, but our experience based on actual use cases is that few times this is really appreciated by the actual use cases. So it's not a real restriction for us. Maybe in some other fields, of course, could be, but not that much for us.
Okay. Oh, any? No, we're good.
Wait.
Was
I'm
it?
sorry, I don't want to have my camera active because I'm not sanitized.
Stena,
Okay.
is that you?
Yes, it's me.
You
I'm
wanted
sorry.
to ask a question?
Yes, I think that in this context, like many other European efforts, one is missing vital points when it comes to future collaboration on the global scale, because one cannot really just presume that just because Europe adapts one of these solutions that automatically the global actors will more or less jump on board as well. And the problem now when it comes to the circular economy side is that the most foundational information supply needed for a circular economy approach in production in Europe is to get vital and important and truthful data from Asian actors and from those actors that are delivering raw materials and components into the European industries. So in a sense, I think that maybe you should work very hard on working with the global actors very early in the process. And this is, I see that the definition of data model here is using JSON, JSON-LD, and those contexts. And that is very flexible and very nice, but when it comes to more complicated approaches, I really see that there will be some problems because many of the solutions that will be needed will be based upon contexts, not individual data entries or entries. They need to be combined together with other types of information to create a functional context for the operation and for the management of the overall situation. So those are just one question and one comment from my side.
Let me answer both of them. Regarding Asian collaboration, I guess you're right, but the smart data models the organization is not only FIWARE Foundation, is the government of India through an agency called IUDX. There is a very large association of cities, EOSC, and the TM Forum, which is a large association of telcos, and around 100 entities which are collaborating. So, and we have held some contacts with Korea, Japan, and some other countries. So in this case, I guess we are quite aware about the worldwide approach. And regarding that context, we are, let's say, quite prepared because we create automatically a context, but this context could be mapped to any ontology. So in every subject, let me show you just one example. These are the elastic, here we are, copy. This context is automatically created for every, because our problem is that there are many ontologies around there, and some of them are rather useful, but few times the ontology will cover all the needs of the use cases. And the extending the ontologies takes a time that is not affordable by the projects. But we can extend the data model in a matter of 1 to 2 days, because everything that we do, but for the single source of truth, the JSON schema is automated. If we cannot make it automatically, we are not doing, because we don't have resources for manually managing this large amount of, there are more than 1,000 data models, and we expect to grow quickly. So basically, we are prepared to the level that we can, because we are not aspiring to become any ontology producer, not at all. This is some other's job, it's not ours. What we are capable of doing is mapping any of our data models with external ontologies like SAR4 buildings or schema.org or IUDX ontology or GCM ontology or whatever. So we are kind of an intermediate step before jumping into ontologies.
Thank you, Alberto, and thank you, Clara. I think we need to move on because we're running, we're a little bit over time. But thank you very much for the interesting presentation. I'd like to move to Pedro Portella, who's from Fraunhofer IWM, and he will introduce the platform Material Digital, which is funded by the German federal government, and its contribution to building the materials commons. Pedro, please.
Thank you, Michela. PowerPoint? Okay. Great. Oh. Are we there now? Fine. Thank you very much for the invitation to present our platform here. And this platform is funded by the German Ministry of Research and Education. And the idea was, since some time, digitalization is a very important issue for the German government. And you know, perhaps Industry 4.0. And the idea of our ministry, of our department in the ministry, was to accompany Industry 4.0 for the area of materials. And they asked us to present or to prepare a platform. You know, actually the points that are given here to motivate the I do not have the pointer. Oh yes, there it is. But just to motivate the idea of materials, of digitalizing the material science and engineering, and to prepare, to give a contribution to the implement of a materials data space. In order to that, the ministry implemented an initiative, Material Digital, and the first step of that was the creation of this platform that we'll present now. And also in a call, there were 13 projects that were selected among 170 proposals that were reached to the ministry, and 13 were chosen, covering very different materials. As you see, we have on steels, on copper alloys, on fiber-reinforced polymers, on glasses, on ceramic materials, and even on cement. That means a very broad spectrum of materials that are covered in this first phase of material. We are now starting the second phase of these projects, which are the classical joint projects of the ministry. And again, we have 10 projects selected to join this 13. And in order to do that, the platform has to be compatible and flexible in order to accommodate all the different issues in each of this project. And you can think it's a consortium between 3 and 7 partners. It's about 20, 25 persons working on those projects, preparing an ontology and workflows from the raw materials till the recycling. It has the complete life cycle of components of each of this class of materials. And our platform tries to accommodate all those developments in a joint project. In the first aspect for the semantic interoperability, given by the ontologies, you can see that those each of these bubbles here represent one of those 13 projects I have seen before, and each of them has a development for ontologies. Some of them very simple, only using the EMO here, but some of others recur to a very different or very large numbers of ontologies prepared by the project own self or to given from the literature and to support that. And if you go further, you can see it screening. And for instance, this one for steel, they have a different basis of that and some of the ontologies that are being developed by the project themselves. And the idea of the platform is to have a common ontology, so that we call that our PMT core ontology, to be the kind of umbrella for all those projects on material science engineering and to map them to the different high-level ontologies and to connect from the high level, from the mid-level as PMTCU core ontology, and to the domain ontologies covering the different aspects that are being discussed in those projects. In this PMTCO, we define 3 main classes for the process, for the processing nodes, I mean for the equipment like furnace or device being applied or being used for these aspects, and for the different objects. And all of them are connected to develop objects. That's the main idea of this PMT core. And due to that, we define the class and the objects going down to the different domains. As we can see here for the next sample, I myself, I am a materials engineer, so that I live actually in this area here where I think of the process that are being done, like the tensile test, and on the values that we determined, like a tensile strength, so that I live in these columns outside to the far right or the far left. And my colleagues developed the ontology, as you see here, those main classes that I defined before, and to define for each of those areas of those levels, to develop the ontologies on this case and interconnecting that from the process. That means the process-based ontology and to define the whole idea like a tensile test going through the different levels of the ontology. We have a repository already with the main ideas of this core ontology. In our website, there are some more details, and we have some publications. This is been accepted for advanced intelligence systems, and this one will be, and we describe here all those ideas in defining this core ontology. I should like to refer to the talk of Hedy earlier today, wherein he mentioned the questions of the existing standards. And it was very important for us in defining those aspects to refer to the existing standards. Like in the case of the tensile test, we went back to the ISO 6892.1 or /1 for the tensile test of metallic materials at room temperature. And if you go through our 92 pages in this standard with a lot of classes or definitions, and the logic of a standard, of the classical standard, is analog. So that you go through 92 pages, and there are very clear definitions with a kind of logics in behind. And went through this 92 pages, we picked every definition, every term that is there, and we prepared a hierarchy, a classification of that. And basically what we have done is a data structure where we define the primary data, the secondary data, and what discussed earlier today also, the metadata. So that we put that, and that was very important, we discussed it, this classification with the colleagues of the technical committee at DIN, which is responsible for the evolution or how to accompany this ISO standard from the German side, and we discussed it with them, what about this classification, so that we define it quite exactly what is defined in the standard for the primary, secondary, and mainly for the metadata. And using this basis. And you can see that is a very definition here for the primary data. There is a definition of time or the definition of force. And along to that definition, given in the standards, we have also the dimension analysis, the symbol being used in the unit. And as that case, for instance, for the extension, which are 6 elements that are defined in the standards, we give this classification and prepare a table with all those primary data for the tensile test to that, and also for the secondary data and metadata. So that based upon this data structure, we prepare an ontology for the tensile test. And what we're doing now is to prepare this data line. That means this is a data pipeline. And if you see here in this column, we have the data in one laboratory. Say at IWM in Freiburg, we go from the tensile test or the universal test machine and also from the microscope measurements for that, or the calibers measuring the diameter of the specimen behind advanced test and advanced test and after the test, so that all those primary data they're collected in one laboratory with one culture. They can be defined, and we put that in a native JSON. That means these are the readable, machine-readable values that are obtained in one laboratory. But if you want now to compare, for instance, IWM in Freiburg or the BAM, one partner of the Material Digital here in Berlin, they had different cultures. So that for the same tensile test, for the same material, you cannot match exactly. One engineer can understand what they have, but machine does not understand how to match the values from 2 different laboratories. So that we have to canonize these results using the ontology. So that if we both agree to use this ontology, then we can match them, and then we have a canonical one can be understood, and from every other laboratories using the same ontology. And then we can put them to map these results and to store them in a triple store. And then you can have effects with the sparkle, and then you go to the last column that we can do the analysis or the simulation or to publish those results. So that's this kind of data pipeline that we're using, and it allows us to make a workflow. In this case here for an experiment, when you go from the model and to project and to prepare the experiment and to go through the validation, collection, analysis, and then you validate and publish the results. This is the classical workflow. And if you put one ontology on the back, we can now provide from the PMD server. And if you use the PMD ontology, we can do this whole workflow from the experiment using the PMD server, collecting data from each step and transferring them to the step forward and using and down. The same way would be for workflow for a simulation aspect. When you have the project and you have here not the equipments, but the applications or the apps that you can use for this kind of simulation. In the platform, we use that for PyIO and the SimStack. Those are the environments that we're using now. And so that you can connect the ontology and workflow for that server, and it's very flexible and reproducible. We can now go one step forward and to use this kind of pipeline for making, for instance, for a simple tensile test, to collect the results, to canonize them, to map, to put in the triple store, and then to select and to show the stress strain diagram and to produce or to calculate, for instance, the elastic models or the yield strength. That will be a very simple case for a demonstrator how this pipeline is being used. The next step is how to put that in a network. So that, for instance, in this case here, we have one PMD central one. That's a notebook that's developed and installed in Karlsruhe in one partner. And the other partners of the Material Digital can use the same notebook. It's reproduced. It's a twin that is being put in our servers. And then we can connect. And there is a first mesh for the platform. And all the other satellites that we have shown before can also connect to this mesh. And we can communicate using this kind of structure. And later on, when we roll out, any other institute or any other industry or company can also access to this mesh and use that. Just to give an idea of the prototype, we are intending to have a Docker where you can put different modules that you want to have, for instance, PyIon and SimStack, and to have a WireGuard to have a safe connection to the central or to the mesh to connect that's inside your firewall, and then you connect through a WireGuard safely to the rest of the mesh. And if we put in another part, that's another firewall here, so that the data, and that's very important for the data property, the real data are really here in this side, so that what's external could be only the metadata, so that you do not have any problem of submitting or to have a share of your data with the rest one. This is only the notebook that this could connect, allows you to have the connection to the rest of the mesh. That's the basic idea of the platform. And now I should give some ideas of one of those products. In this case, here is Glass Digital. It's one of those products that's doing with the glass, the whole glass cycle. And this robot or this station here for the glass melting was developed by the Fraunhofer Institute in Würzburg, ISC, and it's installed at BAM. And what you see is that there is a mixing station or a dosing station preparing that to put the raw materials in the crucible. The robot can mix it okay, and it puts in the furnace. It's again. This is only for the preparing. It's only for the first stage from the preparing from the raw materials to the glass. After that, we have a high throughput characterization, and the data are deposited in a repository with an ontology on the back, and can be used to prepare a digital twin and to put them in a database. And this database is again the basis for the design processes of new glasses, so that you can complete the whole cycle in this. And you see here all the partners that are involved in Glass Digital, and in preparing from the glass design to the classification of the glass that's being poured and to have the experiment. The data pipeline for Glass Digital is exactly the same I have shown you before. The data are produced here. They are canonized in this JSON paper to map it and to put into the app and being this available for whole community, so that it can be used for an external user in order to design their own glasses and to prepare a digital twin for those glasses. That means the same idea of the pipeline I have shown before is being used here for Glass Digital. The ontology that's based in a former version, it's been adapted now for the new version of the PMD core ontology, but we have the same concept that is being done. And what you see here, the ontology covers the whole process from the raw material, from the manufacturer, the characterization of that, and then also from the values that are being selected and deposited, and can also cover the different aspects from the manufacturing, even for a glass, or in the crystallization, in the case of have a glass ceramic. That's, in a very short message, our idea of the platform Material Digital. You have our contact in the middle, and for the case of glass, my colleague Klaus Miller in Berlin. Thank you very much.
Does anyone have any questions for Pedro? Arco?
Very good project, impressive. However, I know that some of these material domain ontologies are being developed or were developed. For example, the EMMO-based ontology suite has covered many aspects. I think BIMMP also has some upper level classes. And do we have yet another ontology for material science?
But perhaps what we do is just to, sorry. We meet frequently, every 2 weeks. There is a meeting of the whole initiative, and we present the developments that are being done in each, and then we discuss it among ourselves. And then to compare. The idea is really to compare and to get this interoperability between the very different approaches or philosophies that each of the partners are being developed. Did I get the point?
Yes, but
Okay.
then it is, I mean, I'm trying to understand what is the requirement to create a new ontology, but not to reuse the existing ontology and to make sure that they are interoperable with each other.
We want to have the interoperability. What we try to do is to match all the different approaches. And the question of reusing is very important, not to just put in the shelf and forget it there, but making the idea of our colleagues to make possible to make the documentation in order to have this not only flexibility, but the universal use for that. And it's very important because since some ideas presented by one group can be used by the next one, so that this it's very fertile because they interact between each other, and some developments that are being done in one group can be used for developments for another group. I think I didn't get the point, but it's only on discussion.
Okay.
Very intensive discussion between very different domains.
Yeah, I understand that is the goal, but then I did not fully capture what is the role of this PMD code ontology in that sense. I mean, why did you develop another ontology called PMD core when there is already these different ontologies there? You could reuse them.
Well, what our feeling was that we, what we're trying to put with the PMD core is just to put different languages. I give an example for the tensile, for the yield strength. If you use for the metallic materials or for polymeric materials or for cement, all they use the same class yield strength, but they understand different things, so that we have to have an ontology that covers all those possibles and to put them together to give the same, to get the same classification. Yeah, okay.
Okay, thank you.
Perhaps we can discuss later.
Yes.
Thank you, Pedro.
Otherwise, we can do it later on. It's okay.
No, maybe it's not so big, so we can do it after the break.
Oh, thank you. Thank you, Pedro. Are we on here and here? Just wanted to make sure. Second. We're back in Teams. So we're going back online now, where Roksana Wilk should be with us. She's leader of Federated Infrastructure Development at SEK CipherNet and involved in the development of EOSC. So Roksana, without further ado, the floor is yours.
Thank you for that. And I have one question. Would it be possible after I finish the phase of the presentation showing to share my screen, or can I even do it now? Because
you should be able to do it now.
I am not. I don't have the possibility to share.
Colleagues are having a look at the moment.
So sorry, but before I start, I can already start my.
Apparently, it's being changed right now.
Thank you.
Try now.
Yes, now it's working. Great. Oh no! Don't do that. Sorry. Of course, I'm working with technology. Can you see my screen?
Yes.
Great. So first of all, thank you very much for inviting me. Second of all, I'm very sorry not to be able to join you in person. And third of all, I'm sorry for my voice. I might be a little not easy to understand because of it, but I will try to do my best. So what I've been trying, or what I will try to present you with, is the notion of EOSC that is being created for many has been created for many years right now, but many people, and I have the privilege to show it to you. And a quick, sorry also because I prepared it in a simple different scope. And then I started listening to all those great presentations and found out that some of the things I would like to share it now will change, because I would like to be more into ontologies and less into showing you the capabilities as they are of the EOSC, even though they are also very important, obviously. But the great thing for me is that for some reason, even though I have nothing to do with your work here, the problems are pretty the same. At least regarding the ontology and functionalities around it. So starting, what is EOSC? EOSC has many, or can have many definitions, but from my understanding, or how I like to promote this, is that is supposed to be in the future a full infrastructure that is supporting cross-disciplinary science. And by supporting cross-disciplinary science, we understand having access to tools and mechanisms and technologies for researchers all over the Europe and world, maybe in the future, that, and this is very important, are able to use it. And this able to use it is a very important element here. And I will tell you soon why. The fun story of this, and this is a project, or this is an initiative funded and supported heavily by the European Commission, and the European Commission came and said, hey, we have a fun idea. You know, there is so many projects going on and developing science, different scientific disciplines for many years now. So it would be fun if you can take it all and make a single uniform environment out of it. Just do it. It will be great. And yes, it's a great goal to achieve, but it's very, very hard. And me personally, apart from taking part in this initiative, I'm also heavily involved in creating a user interface to it, to this environment, to this initiative, namely the marketplace. And this will be also important in this presentation. So from the who are we making it for? We are making it for the researchers mainly, but all people that want to have its own brick added to the scientific world, and with the use of digital tools. Because nowadays, and this is also our way of understanding, what we are also working with is open science, or the idea of open science. And for open science to work better, we can create new technologies, new tools to support it. So the rules supported with open science can be automated and easily accessible from the user perspective. And on the other hand, once the science is more open, it gives a better opportunity to develop technology itself. So it's like, you know, one is working for the other and the other way around. So in this world, we are having this user of digital tools, digital solutions that is coming and trying, based on the goal that this person is trying to achieve, or a problem that this person is trying to solve. That's the main gist. This person wants to solve a problem, but not necessarily knows what is out there to solve it. In initiative like ours or yours, we tend to work with people who at least know a little bit about the area of work, about the technical stuff. Most of the researchers out there, and citizen scientists even more, maybe not the young ones, because they have technology like born or typed into their blood cells. But most of the researchers, they are not knowledgeable about the technology supporting science nowadays. So what we need to do is create an ontology that is understandable enough for the researcher, for the user to find for the discoverability purposes, but at the same time, because the purpose is there is someone coming to ask for something and someone other, we call it a provider, needs to give that something to the researcher. And once the researcher using our ontology defines what is needed, the provider must know what is supposed to be delivered. So exactly, we need to know the answer to the question, what should the researcher select? And once the selection is done, how they can, these various tools can, if they can, work with each other, and if so, how? Sorry. Why it's not changing? So the story of EOSC started with big European infrastructure that are mostly about exposing data, and this is what the scientists and, as we know all, we are seeking for mostly, but also infrastructure giving the infrastructure services supporting the processing of this data. And now, the EOSC has a goal to create an architecture that supports delivery of these tools in a user-friendly manner, ready to be used almost on demand for any purpose possible. Again, it's great, I love it. And now, what we have right now is this architecture that consists of two main ideas, EOSC Core and EOSC Exchange. And EOSC Core is a set of services, core services, that are supporting professional delivery of services. I am coming from the infrastructure world, which some time ago, like 10 years ago, maybe a little bit more, was taught that once you are delivering services, computational services, we want them to be about quality. And for them to be about quality, we need to have certain supporting services around them, services like accounting, monitoring, access to those services based on AI infrastructure, access policies that are supported with order management. We call it order management, but in other infrastructure, it's called, for example, resource access. I'm sorry, I forgot right now. I will just move forward. And tools making those services discoverable, like marketplaces. So we came with the services to EOSC world, but in addition to services, we have also the data that also can be about monitoring, the accounting of the usage, and many, many other important things. So this is the core services that support professional delivery of objects, we call them resources, that might be interesting from the researcher or scientific point of view. And then is the EOSC Exchange, which is the content of EOSC catalog, the services and all the research products that the researcher might ask for. And these are the resources that we call them providers, are coming with, adding to the catalog. And when they want to add them to the catalog, they need to, there is also a notion of horizontal services. It's also kind of important. These are the services that are supposed to be able to support any type of science, like science or even thematic services, because this is also an important thing. How science has been evolving mostly right now was kind of scientific discipline centric. It started small, and by small I mean narrow rather than small. So it was specific, and then we are trying to be cross-disciplinary more and more. And there is this fun anecdote that you probably know about a guy from Nintendo who used to be some common technical operator, and he promoted this horizontal way of thinking, or at least this is the anecdote that pops up very often when you speak about horizontal way of thinking. So that probably because he was not very good at sophisticated technologies around video games, but he knew a lot about electronics, for example, and he could transfer the knowledge and some problem-solving mechanism from his area of interest into this new one. So reusing of solutions from one area onto the other. And that's also one of the things that in the end we want to make possible, at least in the scope of interdisciplinarity in EOSC. But again, it's not as easy as we would wish it to be. So once the researcher is coming and hopefully, and I will show you this in a second, hopefully successfully finds what is needed, there are different types of resources that can be added or chosen by the researcher. They can be added, ask for permission to start using them, and then start using them, and hopefully it's all open access, but it's not most of the cases, but not always. And then hopefully the researcher can achieve the goal he had at the very beginning. And now, after a while of investigating what in fact we have in our catalog, we found out one thing that for me it's one of the lessons learned, important ones. I've been working with ontology without knowing it for many, many years now. I think that from the very beginning of being involved in EOSC. And there was a question in the chat right before I started talking. Why no reusing the ontology? Why thinking about new ontology instead of reusing the already existing ones? It's a very fair question, but I have, in my opinion, a good answer to it, or at least the answer that was relevant in my use case. The ontology I need to make these things work depends on the function I want it to support. And the functions of the ontology I need to apply to the EOSC resources needs to support three important functions: discoverability, order management, so possibility to adequately reflect what is the access policy of a given resource, and composability. And composability is the greatest one of them. Because when we are talking about composability, in our case, it's mostly about composability that is close to the data life cycle. So data, as we understand, for example, numeric data for a mathematician that wants to, okay, I don't know what mathematicians do really. So sorry. So trying to solve the dark matter problem. So having loads of data, trying to make sense out of them with the use of huge computational resources, tools to process the data, storage to back up the results, and then services capable of publishing the results for our fellow researchers in dark matter. So this data life cycle is relevant to the dark matter scientists. But as, for example, Pablo has shown, he's shown another life cycle of a data as I know it. And it's a different one. It doesn't imply as many bricks as I'm showing you right now, maybe here, but it has some other bricks that are not visible here. So in the end, my ontology needs to support that many different use cases of possible data lifecycle. In our EOSC world, and another lesson learned, we tried, or I've tried at the beginning of being in or designing the EOSC marketplace, I've tried to understand the big picture. Because this is also, it has also been said that we are now harvesting big numbers of repositories and other sources of data. So in our catalog, we have billions, if I'm not mistaken, but millions for sure, of data records. And they are coming from different disciplines to different countries, different policy makers, different funding bodies. All of these aspects have a say when it comes to the ontology definition. So what we tried to do, for the sake, we started with discoverability. What we try to do is have one ontology, the very general one that allows the person to filter the first step of filtering of this whole big database of possibilities out there and find at least, I don't know, 10,000 hits instead of this 20 millions. So first of all, we delivered something we call a resource profile. And I will, after my talk, I will share the link to a public record of it from EOSC Future project. A resource profile that is supposed to be this first this high-level ontology for EOSC resources that allows users who probably not know a lot what they want to search for. They somehow know, they know from scientific discipline they are, so they can tell the most I don't want to say obvious, but I will. The most obvious characteristics of them as researchers. And then they will have more specific hits. And then when you go to a given data source, for example, as we know, then the metadata schemas are getting more and more diverse and more detailed. We've been trying to catch all of these aspects from the very beginning, but we very soon recognize that it's impossible because the picture is too big, simply. So our second lessons learned was go, and it was only in case of discovery, go use case by use case. And then we also learned that this approach was working for us in every new adventure we were taking. Why is it not changing? So coming to catalog and marketplace, I want to show you very quickly.
So sorry to cut in, Roksana. We have about a couple of minutes left on your time slot, so maybe you can just speed up, like zoom through the last few points.
Well, exactly last few. In fact, this is what I wanted to focus on because the last few were not as relevant to the ontology part as this one.
Okay, brilliant. Yeah.
So again, what you can see is the implementation on the user part of the ontology, the general ontology of EOSC resources. By EOSC resources, we understand different forms of it, like software, services, publications, data sources, training materials. But we also very quickly found out that our users don't speak that language. They more speak a goal-oriented language. So we moved to another way of a new ontology, really. Maybe not ontology, this was only a part of it, but a new way of presenting for the sake of discoverability, more related with the activities performed by the researchers. And then we are going deeper. Then we are presented with the fuller version of the ontology we created now for the sake of resources. And when you find something from a given category, especially scientific domain, then you can go inside of it and work within a given field. And there is the link to it if you want to check it out later. And when you are joining EOSC as a provider, so if you want to share either your data or your tools supporting data processing, you can ask EOSC for the supporting services like help desk, accounting, and so on, and integrate with them for the sake of better delivery of your services or better delivery of your data. And this is the part where I wanted to talk a little bit about the core services, but I think I will skip that. And I will only say one more thing about the mapping part. And it applies especially for the data, to the data part. As you probably well know, there are different ways to describe data depending on the group of people who are dealing with the data. What we have tried so far to do with that many, it's only 2 million, 2 million results of data itself, we tried to automate the mapping. So automate based on analysis of the language itself, because in some ontologies it was only about some minor differences in the names of parameters. Sometimes you can use AI to, even if the name of the parameter is totally different, but based on the values it can have, you can automatically check that this might be the same parameter in two different ontologies. We have other crosses or bridges, sorry, between or tools supporting the translation of the ontologies, but still it's not enough, because there is also one big problem. People who are filling in or creating the metadata for a given object. So we can have the best ontology that supports every function, every use case we want for the sake of our infrastructure, but it still cannot serve the user value if people are misfilling the information. So for example, many occasions, something is labeled as open access, and when you try, like this one, and then you try to open it, and you cannot, unless you have a account created in a given university. It won't be the case probably because it's Zenodo, but it happens a lot. And a second thing, and the last thing before I finish, is that for us, and it's a nightmare, for now, the best way to curate the data is to work manually on it, at least for this part of data that we care the most about. But in parallel to that, it's spreading the skills and knowledge. This is the absolute most important thing for us, that if we want the ontologies to work, even if we come up with the best ontology ever, for data schema to be usable, we need the data itself to be good. And to data itself to be good, we need to teach people how to define it, how to create it. So that's the last thing I wanted to say in this presentation. And thank you for this opportunity. Exit full screen, sorry. If you want to contact me for any smart diagrams or anything, because I have those as well, you can contact me under this one, or you can contact our experts via the EOSC marketplace, for example. Thank you very much.
Thank you, Roksana. Any questions for Roksana? I think they are overwhelmed.
Sorry.
So thank you. It was a tremendous amount of information, more than I've got from EOSC, having actually had quite a lot to do with it myself as well. Roksana is obviously providing her contact details if anybody wishes to discuss it with her. And I will now welcome Tobias Huschle, who's with us in the room. He's from Fraunhofer IWM, and he specializes in material informatics and focuses on ontology development based on EMMO. So Tobias, welcome.
Thank you, and hello again. So I already was introduced. I set my timer so we don't lose too much time anymore. So my name is Tobias Huschle. I'm working at the Fraunhofer IWM in Freiburg, and today I want to present you a quite practical introduction into our data space management system. So after all these theoretical things we discussed today, now I want to show you based on the example of an PMD project. We already also got the introduction from Pietro somewhere here. And so I want to show you a demonstrator for the semantic data integration using the data space management system. This is a product developed by us at the Fraunhofer IWM. And I wanted to start with why we need semantic data, but I think we... okay. Thanks for the reminder. So now everybody at home should see my screen. Yeah, so I wanted to start with why do we need semantic data, but I think we already heard a lot about fairness of data, and these arguments are maybe already mentioned today. So just a quick overview, and maybe from the focus of our material science domain. So in our material science domain, there's a huge range of subdomains which all have some various requirements. Then there's a large volume of data. This could be, for example, experimental data, simulation data, or at least some literature data, and everything is stored in different silos. I need to bring in my pointer. In different data silos that are not connected. And also another issue is that the data is very often really heterogeneous, and like it is in Excel, stored in Excel, JSON, CSV, or maybe even in PDF. Yeah, so the challenges here is the limited access to the existing data and the high number of tailored solutions if you want to make them compatible with each other. And that requires a huge amount of resources. Our goal is to increase the interoperability, so breaking up the silos and provide some data-driven decision-making. The solution we want to take here is the semantic data integration with using ontology-driven tools like, for example, triple stores and so on. So in the material science, there are some easy questions like even this one. So which materials are already tested? So when the tests are maybe 10 years, 15 years back in the past, it's not easy to retrieve the data. I think a lot of you already had this experience. And maybe some more advanced questions like what is the correlation between the carbon weight fraction or the tensile strength? So two parameters that you measure a lot, but yeah, you need to find the data at first before you can do these calculations. And yeah, for this example, I want to show you the demonstrator, or for example, like this. And here at first, I want to show you how a classical workflow for scientific data processing is. So you see here on the left side, there's a typical process chain that all generate some data here in form of maybe Excel files, for example. This is in our use case here from the Kupfer Digital project. And then the first step is you need to read in the data. So you can do this with maybe some Python scripts, or maybe even better, you can copy paste it manually from an Excel file to another one. So I think everyone sees this in the daily work. And so then you have to read in data, but then you still have no structure in it. You don't know the meaning of this data. So you need to provide another Python script, for example, to bring the data in shape. Then you need maybe some other processing like data cleaning, for example. And then you are finally at a step where you can say, okay, now I have a benefit from the data. So you see here at the bottom, the data scientist has already a lot of work done until he can provide some, for example, some dashboards or some figures to the material scientists. And yeah, here on the top, you see a quote, so that only 20% of data analysts' work is for data analysis, and the 80% are for finding data, cleaning data, and so on. And we want to improve that. And we provide a framework called the DSMS, the Data Space Management System. And where all these tailor-made solutions were in the slide before, we have a framework where you can incorporate all these different Python scripts, for example, and reuse them for several projects and make them accessible for others, not just for you. And so in our example, we still have the data and the process chain where the data is generated and the data from different sources. And the first step is we need to transform it. So we use a data to RDF pipeline in our case that we can run inside the DSMS. So the user in the end won't see anything of this. And this can be modular. This can be replaced by other pipelines, for example, to process the data. Then another part of the data space management system is the data storage. So in our case, we use Allegro Graph database, and there we store these now structured data enriched with semantic meanings, and they provide an easy access for the user. Then we also have here a Sparkle endpoint. I think most of you are familiar with that one. So with these, with the Sparkle query language, you can access triple stores and get the data, and with the data you can run some applications. You can also provide in the DSMS for the users. So the material scientists, you will see it in the live demonstration right now, can easily just upload the data. It will be automatically converted, and they can access it and benefit from the now easy access and concentrate on their work. So another thing from the DSMS, you see you can split up the roles depending on what is the background of the user. For example, you have here on the top a system administration guy who is responsible for setting up the system. Then you have application administration. So someone who is able to program like in Jupyter or in other Python scripts, and also has some knowledge. So he is the intersection between the domain knowledge and the computer science, I would say. And at the lower end, you have just a user who is just interested in, I want easy and fast access to data that I need for my daily work. I don't want to think about all the steps between. I just want to access these things. And so you can differentiate, and for example, the user doesn't need to care about all these Python scripts in the background. Now let's go to the example. So here we have an example data set from the BAM, the Bundesanstalt für Materialforschung. I hope that was right. And from the Kupfer Digital project. So as I said, in the also in the PMD framework. So you see the data is split in two categories. So the metadata for general information to reproduce the experiment, like machine information and so on, and the measurement data in the background itself, like in our case, the hardness values or some other parameters and data that was generated through this process. Then I will just jump over this one. So we also need some ontology development. So the ontology provide a data schema for the later data retrieving. Just for information, we use the EMO and other top level or domain level ontology in that framework, like the Cameo and the mechanical testing ontology. Okay, now let's go to the live demonstration. I will take the risk for a live demonstration and hope it works. I already opened it, but it seemed to be closed again. No, here I was just in the wrong one. So here you see the user interface of the DSMS, and you see I'm already logged in. I need to refresh the page to see. Okay, I'm not logged in, so we can do this process. So you see there's a user management. You can also use GitLab for that. So I'm quickly logging in, and now I have several options. And within the user management, there's also, you see here, I'm now an administrator, so I have some additional rights. As you saw in this role, I'm now the guy in the middle, so the application administrator. Now I want to enable people to upload data. So at first I need to create a new data set profile. A data set profile defines how is the data, or what kind of data do I want to push, which scripts I need to trigger in the background, and how can I process them. So I make here the Onto Commons data set profile. It doesn't matter for this example. So now I'm directly in the data set profile, and I have here several settings. So for example, at first I can I can map this dataset profile to an ontology or taxonomy that is in the background, so I can find datasets easy. Now we are talking here about indentation testing, so I'm just choosing that one. I will show this to you later where we need this one again. So then the next step is I can choose here my script to process the data in the background. So this is now linked to this dataset profile. And in the end, we want to process the data. We want to get some information out of it. So I have here based on Python, voila, a dashboard, so the user can access it. So I call it dashboard. Okay, now we have everything, I hope. I hope that wasn't too fast and I forgot something. So now I can go back to upload again and see here's my OntoCommons dataset profile that I just created, and now I want to upload the data itself. So I call it again OntoCommons. I'm not too creative now, and here we go again. It looks quite similar, but I don't have that much options to create. So I just can upload the data. So now I want to navigate to the data set. Let's go here. So this is an Excel file, as you can see, and I can just drag and drop it here and run the script. Now it loads. And I have 2 minutes left. I think that that's maybe enough for a quick run. So, okay, it worked. So now I'm accessing the dashboard. So this is the application. You can write whatever application you want to, and you can exchange it for every use case you want to show. And now you see I can access the data without any use of code for the material scientists who don't want to write code. And I can say here, give me the some parameters of the measurement. I'm just choosing here the hardness, the diameter, and the material. Then I click on Get Data, and I already have here a list of data and the values. Now I want in the next step to get a better overview over all this data and want to do a correlation analysis. So here it is a trivial example, so the correlation is quite high. So, but this is the data set I can show you today. And for deeper insights, I can say, give me a diagram of all of that, and I can directly plot it. So you see, I uploaded now in just a few seconds or less than a minute some data set, and can retrieve it, can process the data. So it's quite easy for material scientists to benefit from the database. So this is now a really small data set, as I said, with not too much meaning, but I think you get the you get the point where I want to go. And then another thing, so 20 seconds left. You have also here the opportunity to explore, like with Sparkle or free text. And here I can search for data that is already in the system. That was the wrong one. I wanted to go to the methods. And if you remember, I said we have indentation testing, and I can apply and search for it. And then I see all the data set that were connected already to that. So it's also quite easy to find data sets that are already in there. And maybe I don't know what I'm searching for. I'm just searching now for indentation measurement. So the last thing then, in the background, so for everyone, we can also discuss this later in detail. You see here is a Jupyter Lab in the background with the scripts that are automatically triggered. You see here for the pipeline that needs to be done once, and so everybody can use it. And same is for this dashboard, and you can replace it by everything you want. So this was just the example today. So, and then I'm at my last slide. So I showed you that the DSMS provides a framework for semantic data integration and data processing that is really modular and flexible for your needs. The benefits of the DSMS are, for example, you can define these different roles. So everybody just need that capabilities that he wants to. If he just wants data, then he can just use the data. Then user management and access control, who can see which data, who has access to it. Then flexible installation of for example, pipelines in that case. Then the integration of applications, in that case, these data analysis application. Then you can provide a really low hurdle for material scientists for scientific data research, because you just need to click to the UI. And the integration of technical innovation in the future, like for example, AI-based text processing, you can also implement there. If it is Python-based, then you can use the DSMS. Okay, thank you for your attention. It was maybe 1.5 minutes too much, but yeah, so.
Exactly at 5 o'clock. Does anyone have any quick questions for Tobias? Or everybody's keen to have a coffee right now, I think, yes. And you can talk over coffee and a snack before we go to the last session of the day, which will be like a real it's a real marathon today, isn't it? Thank you, everyone, and thank you. And let's have some coffee and for the next. Is it 15 minutes? Are we taking 15 minutes or? Are we taking 10 minutes? 10 minutes? 10 minutes, everyone.